Okay, I feel like we can proceed. So, hello everyone, welcome to Ask Seminar series. This is John, the seminar coordinator. I will be moderating the seminar with Kathy Medley, our communication manager, and couple of housekeeping things. So, usually our director joins us and introduce the speaker, but today he has another meeting, so he cannot make it. So our communication manager, Kathy, will be introducing the speaker. And just so you know, then this seminar is being recorded and we will post the video on our YouTube channel. And after the presentation, we'll have the Q&A session. So please feel free to bring up any questions you may have. And we encourage you to unmute yourself and speak up. If you don't have a mic, you can chat us the questions and Kathy will read it out. So before the speaker gets started, so I will have the Kathy to introduce the speaker. So Kathy, please go ahead.
Thanks, John. So I'm excited to introduce our speaker, Elie Bou-Zeid. Elie is professor of civil and environmental engineering at Princeton University, where he also served as the founding director of the Metropolis Initiative for Urban Technology until 2022. His research broadly examines flow and turbulence in the atmospheric boundary layer, with a focus on heterogeneous and unsteady flows and on applications related to cities, renewable energy, and hydrometeorology. Bou-Zeid is the current chair of the Committee on Boundary Layers and Turbulence of the American Meteorological Society. He previously served as editor of the Journal of Atmospheric Sciences. He is a recipient of the 2025 Atmospheric Sciences Ascent Award from the American Geophysical Union and the 2026 Helmut E. Landsberg Award from AMS. So Elie, please give us your talk. Thank you for being here.
Thanks, Kazi and John, for inviting me and introducing me. Thanks, everyone, for coming. So my talk today is going to focus mostly on cities and basically their role in the broader Earth system. So I want to focus on this new sphere that is emerging, the Polisphere, and how in that Polisphere, nature, humans, and infrastructure are shaping an emerging Earth system. So I have to first acknowledge all my current and previous students and postdoc who did most of the heavy lifting and most of the work that you see their names here. And if you want to know more about our work, please go to our website. So, okay, so what is the Polisphere? This is Shanghai from 1980 till 2010. You see the very rapid change and the drastic change in the surface of the city as the city urbanized very extensively and intensively. So basically, when land use changes from basically natural to maybe a low density like Shanghai was in 1980 to a very high density like it is today, there's a new environment that's created. The surfaces, the air layers, the water body, even the snow cover dynamics are very different from anything or any natural system. And they're largely controlled by human design and activities. So they really create a new kind of Earth system. I like to think of it as an Earth system that basically has its own characteristics and that we need to study. Now, this Polisphere also is expanding. So this is, for example, how over 100 years Phoenix expanded from a small town around 1912 to basically a very large metropolis that it is today. So urbanization is continuing to rise, and cities are continuing to grow larger and larger in the global north as well as the global south. So basically, it is kind of a worldwide or global trend that we have today. Now, why is it important? Why do we need to study the Polisphere in cities? So according to the 2025 revision of the World Urbanization Prospect, about 80% of the world population now lives in cities or towns, towns being defined as having population between 5 and 50,000 and city over 50,000. So basically 80% of the world population now lives in some sort of a built terrain. Because they tend to be more affluent than rural residents in most of the world, they consume even a more than 80% of the energy, and they're responsible for the emission of more than 80% of the greenhouse gases. So it's very important to understand what's happening in this polysphere, because cities are where the grand challenges of the future will be overcome or maybe won't overcome. And obviously, we would like to overcome them. We want like cities that look like the upper picture. So we need to understand how physical and chemical processes interact in cities and how cities basically behave. So double click. Let me just actually use a pointer here. Okay. Okay. So when we think about basically cities, we need to model typically the physical processes and sometimes even the chemical processes that are occurring. But one of the challenges is that there are a lot of processes, and also they occur at very large range of scales. So we can start at the smallest scale with what happens at the droplet scale, maybe a droplet that's sitting on a leaf and basically waiting to evaporate. And then we can go to basically processes that are on the scale of a building, processes that are on the scale of a neighborhood or a city, and then we can even go larger and look at city in the context of regional climates and regional weather systems, and also city at the global planetary scale. Now, obviously, we cannot kind of study all this range of scale or model all this range of scale in one go. So what we tend to do is often we tend to try to okay, let me just change this back. Sorry, I'm having problem advancing my slides for some reason. So I'm gonna go back to not a pointer. So typically what we need to do is then divide this range of scales into sub ranges or separate ranges. And typically one convenient way when we think about urban climates is to think about the micro scales that I am showing you on the left. These involves again everything that's happening on the scale of a building. On the right, I mean on the scale of a building, the turbulent eddies in the atmospheric boundary layer, and so on. And these are the micro and local scale. If we want to model them, we would use something, for example, like a large eddy simulation. On the other hand, on the left, what we have is basically the synoptic and global scales, where basically, if we want to model these, the resolution of the models will be quite coarse. And so we will not be able to resolve any of the small scale processes. So typically, when we do this, we are trying basically to think about the right side of this picture. We want to see how we can model and observe the fine scale processes. And then once we understand and can basically model these fine scale processes, then we want to think about how we can represent them in the coarser simulations on the left, where basically the buildings are unresolved and a lot of the turbulent eddies are unresolved. So how we can parameterize the impact of city and weather and climate models. So we work a lot in my lab on all the micro scale and local scale processes on the right, but today my lecture is mainly going to be focused on kind of how we go from the left to the right, from the right to the left to some extent. So mostly I'll focus on representing cities in basically large-scale models. But when we think about representing cities or modeling cities, whether at the local scale or the global scale, we have to kind of keep in mind to what end. So what is the goal that we are trying to reach? So to understand or to frame these goals better, it would be useful to kind of go back to a little bit in history to see why we started basically trying to understand and model Earth systems and geophysics. So the earliest endeavors to understand Earth systems basically aimed to kind of describe what's happening. So one of the first documentation of urban impact on the microclimate was by Luke Howard in his book on the climate of London. And what he did is collect a lot of data and basically plot these data, and so describe or document basically the environment in London at that time. So it was purely descriptive. And then the first attempt to not only describe what happened in the past, but to predict what happened in the future, the first attempt to integrate these budget equations of mass, momentum, and energy to predict the future was done by Lewis Fry Richardson. And actually, it failed due to basically poor data assimilation or inappropriate data assimilation at that time. But his 1922 book basically laid the mathematical foundation of everything we do today in terms of weather and even climate modeling. At that time, again, we were not trying to understand the physics as well as much as kind of describe them and then predict them. And then we got a little bit more greedy, so we wanted to understand why things happen the way they do. So the first successful attempt to model the whole Earth climate system numerically was by Sukiru Manabe at GFDL. And if you read that paper, actually, and if you have talked to Suki or have attended one of his talks, you will quickly realize that the reason he wanted to develop this model is not so much as to predict the future climate. In fact, at that time, climate change was not a hot topic. We didn't know the extent maybe of the damage it could cause. So those early models were really diagnostic. They were trying to understand how the climate system works rather than to predict it. So we wanted to understand the fundamental physics. So in a sense, if you think about the progression, we went from descriptive model that told us what happened to predictive model that tell us what will happen in the future and give us some foresight, and eventually to diagnostic models that can also tell us why does something happen or not happen. Now, if you think of where we are today, in fact, we're even getting a little bit more ambitious. So if you look at the latest modern Earth system models, they don't only want to diagnose or predict, they want to do a little bit more. So today, what we try to do with modern Earth system models is to capture what we think are the main interaction between the various systems. We then also try to capture all anthropogenic effects from land use modification to greenhouse gas emissions. We try increasingly to resolve cities or basically represent their impact at the global scale. But most importantly, we are also trying to use these models in a prescriptive way. So we want to use them to prescribe pathways to attain desirable futures. So what should we do, for example, to limit global warming to 1.5 degrees or 2 degrees? What happens if we can reduce or if we can't reduce greenhouse gases? So we know we have a solution and we want to give kind of a prescription like a doctor would give a prescription to that problem that we may face in the future. So increasingly, this modeling is getting to the point of trying to develop prescriptive models that can help us say how we can make something happen or in fact not happen. And when we think about cities, this is extremely important because we need prescriptive models. We need to think about how we can design, plan, and manage cities better in the future. So having this prescriptive capability is very important. So if we want to have this prescriptive capability, we need to be able to essentially describe cities very well in models at all scales. So the first question is then, what is so different about built terrain compared to natural terrain that makes it so unique? The first attribute is the urban form, the urban geometry, that basically results from the roughness of the buildings. That as we will see, is basically imposes large drag and traps pollutants and radiation in the city. So the first one is related to geometry. The second important attribute is urban function. So what we do in cities, we burn fossil fuels, we have economic activity. So this is a thermal picture of a highway. And you basically see all the hot cars because, of course, the combustion in the cars raises their temperature and creates anthropogenic emissions related to all this function. And finally, we can think of the urban fabric, which is the type of material that we use in cities that are really unique. Concrete and asphalt, for example, have no natural counterpart with the same properties. So these three F's, the form, function, and fabric, are what make cities very unique in terms of a location or system. On top of that, when we think about cities, we need to think about how they are basically immersed in the global environmental change that the planet is undergoing, and what is their impact on this environmental change, and what's also the impact of that environmental change on urban environments. So practically, how do these form, function, and fabric result in physical processes or forcings that cause cities to, for example, overheat? So the main drivers of urban-rural environmental differences, for example, if you think in terms of temperature, would be radiative. So in cities, we use darker surfaces like asphalt that have very low albedo and absorb a lot of the radiation that is incoming. And also because of the form, we can have geometric trapping. So typically, a shortwave ray that is impinging on a roof or on a flat surface will be reflected back to the atmosphere. But if it impinges on a wall, it has a good chance of being reflected downwards and absorbed again. So that photon has another chance of being absorbed, which increases the actual or effective albedo of the city. There's also material drivers of that difference. For example, concrete is a very effective storer of heat that basically can stay warm well into the night, and it's the cause of urban overheating during the nighttime. There's also a lot of metabolic drivers related to the function, so the human activities such as space heating or cooling or combustion that release a lot of anthropogenic heat and pollution. There's also the geometric factors that are again related to the form. These are the complex surfaces that not only trap radiation, but also slow the wind and can cause basically trapping of pollutants and of basically polluted and hot air in the city. There's also a very important set of eco-hydrological drivers that I'm going to come back to today. So the lack of pervious soils, the reduced vegetation and surface water in city, reduced evapotranspiration and cooling, and that actually ends up being a very significant driver of urban overheating. And also that ends up resulting in biogenic emissions that may be very different from the natural terrain. So this is basically the picture. Below is a illustration of all the processes that maybe affect surface temperature. But if we also think about urban air quality, we kind of get the same, or a similar story, where basically we have strong emissions of pollutants in the cities, outdoors and indoors, and we have all this pollutant trapping and biogenic emissions that basically alter atmospheric chemistry and air pollution in cities. So as a result of these kind of drivers of environmental change at the local scale in cities, we know that cities generate urban heat islands, and that also results in urban overheating in the summer that basically can have severe economic and health impacts. Cities also, it's well documented now that they modify precipitation and urban water cycle, and they result in unhealthy air quality. Now, these are kind of the local environmental change results of land use change or of urbanization. But what we also know about the global warming and the global environmental change is that at the global scale, we expect heat waves to intensify and become longer. We also anticipate that greenhouse gas induced global warming is going to change precipitation and evaporation patterns, and it's also leading to a global a change in global atmospheric chemistry and also in biogenic pollution. So now we have kind of the greenhouse gas global change on the right and the land use urbanization linked changes on the left. And it's important to basically represent cities in global models, because what we truly would like to do is to understand how these impacts, the local and the global, interact, especially during, at the higher tails, during the extremes. We want to understand if there will be positive or negative or no feedbacks between the global and the local. And we want to also, when we think about solutions, we want to try to mitigate them and find solutions maybe that address them simultaneously. So this is why kind of understanding cities and how it interacts, or basically the polysphere and how it interacts with the larger Earth system is extremely important. So how do we do that? So typically, when we want to represent city in a global climate model or in a weather model, typically we use something called an urban canopy model. So the idea here is that most streets are much longer than they are wide. So the width and height of the street are much smaller than its length. So we can think of a very long, in some sense, an infinite canyon. And that infinite canyon is composed of two buildings of the same height and the cavity between them, which is the street air, and the roofs, and basically all the buildings and what's happening inside the buildings. So what we typically are going to try to do is to solve the surface energy budget for each facet separately. This consists of the Q star, which is the net radiation, which is then partitioned at every facet into a sensible heat flux, a latent heat flux, and a ground heat flux that goes into the ground or maybe into the building. And when we started working with the earlier urban canopy models about 15 years ago, it was clear that they were severely lacking in terms of representation of hydrological processes. In the last 2 decades, I think the community has come a long way, but at that time, the eco-hydrology was very poorly represented, with no grass between the buildings and no trees. So one of the first things we started doing with these urban canopy models is trying to improve the representation of eco-hydrology. This includes trees and vegetation, but this also includes water budget for urban soils, as well as for impervious surfaces. So after a rainfall, there's going to be potentially a significant layer of residual liquid water that can then evaporate, and that is going to be important for determining, for example, energy partitioning in the city. So we included all the water budgets for the various facets. We also wanted to be able to resolve subfacets that may be heterogeneous. For example, in this case, this roof we represented as being half green, half black. So if we have partially green, partially black, partially white roofs, or maybe, sorry, I don't know why the slides are behaving the way they are. Basically, if we have a wall that is maybe partially glass, partially concrete, we also want to be able to represent that heterogeneity. So what we did is allow basically the model to have heterogeneity at the subfacet scales, and then we also wanted to basically represent the material properties, which are extremely important, the thermal and hydrothermal properties of the material, very well. So we did a lot of developments to these urban canopy model, resulting in what we call the Princeton urban canopy model, that we basically explain a little bit in some of these papers. And so the first thing you want to do is to start by validating the model. So in this figure, what I show is a validation of the ability of the model to reproduce surface states, so surface temperature in this case. We had a sensor network over the Princeton campus where we were measuring the surface temperature over asphalt, concrete, and vegetation. So the markers here are the observations, and the lines are the model results. And you see that the model actually tracks the observations quite well. Now, when I say a model tracks observations quite well, that's a very kind of qualitative statement. Specifically, what we wanted to do is check that the model errors or the uncertainty is smaller than the signal that we are trying to basically analyze and explain. In this case, what we were trying to do is to see how the different properties of the material results in different surface temperature. So the signal is the difference in temperature between asphalt, concrete, and vegetation. And if this is the signal that you are trying to resolve, then it's clear that the model error here are smaller than that signal. So we have a favorable signal to noise ratio to try to understand the impact of material properties. In this case, also, this is a validation not too far from you, University of Maryland at basically UMD. This is on the campus of UMBC, where basically we had an eddy covariance station operated by my colleague Claire Welty. And so what we did in this case is basically take the observations from the eddy covariance tower, which are in blue, and basically try to model the fluxes. And again, you see that the observations have a little bit more variability, but overall, the model captures the trends of the surface fluxes quite well. Interestingly, also after, for example, this rainfall, what you see is a significant drop in the sensible heat flux that was accompanied by an increase in the latent heat flux that I'm not going to show you today. But again, you see that the model is able to represent fluxes quite well. Now, our most recent effort by my ex-postdoc, Enar Azan, who's now a professor at the University of Pennsylvania, was to take this 1D or 1.0D, if you want, urban canopy model and make it into a 2D model. So in this case, basically, we are modeling all of Brooklyn. And on the right, you see the prediction of our two-dimensional Princeton urban canopy model. And on the left, you see Landsat, and you actually see that there is a reasonable agreement between the two. This is at the 100-meter scale, and PUCM clearly captures the variability at the 100-meter. Landsat claims that they have a resolution of 30-meter, or maybe the native would be 90-meter. But you do actually, if you analyze even the spectrum, you see that it's a little bit coarser than that in reality. And it doesn't resolve, for example, it cannot see specific streets as well. But overall, the patterns are captured quite nicely. Also, what we are analyzing in this forthcoming paper with Enara is the role of rainfall and what aspects of rainfall we need to capture. So when it rains, obviously there is evaporation that will happen in the long term, but also very shortly after rainfall, what will happen is you're going to have a runoff. And that runoff is going to pick up a lot of the heat that was stored in the subsurface and basically advect it away into streams or culverts or pipes, and will cool the surface very rapidly, not by evaporation, but by this quenching effect. So in this case, what we did is run the model with quenching and water storage that will sustain evaporation, and then without quenching and without water storage, so removing the hydrological realism of the model. And you see that there's a big difference in the observations are in black, and the model with surface quenching and water storage reproduces the results, the observed results much better. And there could be up to a 10-degree difference. This is a 10-degree cooling by the evaporation and the quenching that is happening in the city and that our model can capture. Now, everything I showed you so far was basically PUCM run offline. What I mean by offline is we run the urban surface model with atmospheric observations. So the observations are coming from a tower or some other source, and it's not really coupled to the atmosphere. But ultimately, what we really want to do is to be able to couple these to the atmosphere. So we have done this, and we've also, so far, we've mainly coupled PUCM with WRF. And in this study, for example, we analyzed the urban heat island of Baltimore, of the Baltimore DC corridor. And what we observe here is, for example, that the PUCM is able to reproduce the large-scale pattern of the urban heat island reasonably well, in terms of the very hot downtowns and the gradual cooling as you go away from the downtown into the rural area. So this is kind of a coupled run of PUCM and WRF. And just a summary of the applications that we had of UCM so far. So in terms of the coupled UCM, we've used it to understand the interaction between UHIs and heat waves, and between UHIs and cold waves, where the urban heat islands are actually beneficial. We also used it to try to forecast extreme heat in cities and spatial variability. And the offline one was also extremely useful because it allowed us basically to understand the impact of material properties and understand, for example, or evaluate urban impact on thermal comfort. But our most recent work has really focused on using the offline and online, or the coupled UCM, to try to evaluate solutions. So we start with cooling solutions, and I'm going to touch on air quality solutions at the end. But in the end, again, we want a prescriptive model. We developed a prescriptive model to develop solutions with it. So what kind of solutions can we think about? So one of the recent solutions that we were very excited about was the idea of retroreflective facets. So let me explain what that is. So typically, if the green is a wall, then if you have these large mirror buildings or mirror facades of buildings, a ray coming in with angle theta is going to be reflected kind of to the other side with the same angle theta. That would be a perfectly mirror-like or specular reflection. Most materials, brick and concrete, are going to give you more of a Lambertian or diffuse reflection, meaning a photon coming in from the sky has theoretically an equal probability of being reflected in all directions. So the reflection go in all directions. And in both of these cases, you see that a lot of the radiative energy is going to go down. And if it goes down, it's going to hit the ground where it's going to be trapped. So one possibility is to basically try to think about retroreflectors, where if the photon is coming in with an angle theta, then most likely, or the most probable reflection is going to be back into the sky exactly from where the photon or the ray came and back into the sky. Now, this is actually not, these are not very, unreasonable or fancy materials. So in your bike, at the back of your bike or your helmet, maybe you have a retroreflector. So they can be made very cheaply. And in this building in Arnhem, you see it as black because basically that building is not reflecting anything into your eyes. It's a retroreflector that was used in this case by the architect purely for kind of aesthetic reasons. So if it's cheap enough to use for aesthetic reasons, then it's probably cheap enough to actually use for maybe more geophysical reasons. And so what we did is basically go into the UCM and modify the way we treat radiation at the wall to allow the representation of these retroreflectors. So in this case, we tried 4 retroreflector prism to glass bead. Prism was the most effective. And what we observe is basically if we have a total reflectivity of about 0.85% for the prism, and the specific retroreflectivity is about half of that. So half of the radiation go back into the sky. So the retroreflectivity in this case is about 0.42. Those are the actual numbers that a prism retroreflective will give you. Then the cooling of the canyon air, assuming an infinitely long canyon here, and that's an important caveat, can be about 2.5 degrees, as you can see here. And on the other hand, if you also treat the ground to be a retroreflector, you're going to also get quite a bit of cooling, in this case also about 2.5 degrees. And the reason, again, is if the radiation is reaching the ground, then basically a retroreflector will not reflect it back to the walls, or the other objects will send it back to the sky, and that allows also the ground to cool quite a bit. So we get a very strong surface cooling as well as cooling of the canyon air that is in close contact with these walls and ground. Now, what's more important is what does that mean in terms of thermal comfort in the city? So in our model, we have a human energy balance model that predicts what the human will feel. The human will basically receive some radiation. There will be conduction C from the core of our bodies. and we're going to cool by evaporation E and convection to the atmosphere K. And so we can use this model to understand what is different about retroreflectors. So the orange line is the skin temperature with a high reflectivity, but not retroreflective, just high reflective facades. The green is the cooling that you get by using retroreflective facades, and here you see a cooling of about over 0.5 degree of the skin, which is extremely significant. And you see that a lot of this cooling was because of the shortwave radiation load that is embedded in RH on the human has decreased quite significantly. Another solution that we got interested in through some colleagues at Arizona State who went and basically did some measurement at various places that were using fine misting in basically that's a common solution in Phoenix to basically cool the atmosphere and make it more tolerable outside. So they did some observations, and we wanted to represent this misting in our PUCM. So here what we again are going to do is add this fine mist into the volume of air between the buildings. This is kind of the 3D view. If you do a cross section looking into the street, we're going to basically continue to have the air exchanged heat and latent and sensible heat with the walls and the ground. But now there is this additional mist that's going to evaporate and cool the canyon air. But also, since water is precious and we cannot mist the whole city, we wanted to take a specific finite length of section along the street and only mist that. So we basically divided our UCM along the canyon into an upwind area that is not misted, a misted area, and a downwind area, and the misted area has a length L. And we're going to basically continue to solve the surface energy budget for all the facets. But now we also are going to basically solve the thermal energy budget of the canyon air, as you can see here. It has all the usual terms that basically we get. This is the heating from the ground, the heating from the wall, the loss of heat at the top of the canyon. But what is unique here is two new terms. There is this evaporative cooling term, Hmist, which is going to be a negative number. That's the conversion of sensible to latent heat as the droplets evaporate and cool the air. And because the canyon is finite, we have this advective term, which is going to basically warm the air in the misted canyon because warmer air goes in than goes out. So the net divergence of this advective term is a net basically warming of the air of the canyon. So with these models, we went now to validate the framework, and these are a comparison of our model to the observations collected by Jenny Vanos and Ariane Middle in Arizona State. And you see that the model captures the cooling as well as the increase in specific humidity of the canyon air reasonably well. Now, if you increase the temperature and, if you decrease the temperature and increase the humidity, one problem is that you might have some offsetting effect in terms of thermal comfort. So we wanted to understand what is the actual impact on thermal comfort in the city. So again, we go back to the human energy model, and we see that there is an additional gain of heat because the atmosphere is more moist. So we are going to evaporate less. However, the drop in surface the surface and air temperature in the canyon are going to reduce significantly the radiative load and basically increase the convective cooling. And so as a result, we get a net drop in the skin temperature by also about 0.5 degrees. This is for Phoenix. For Houston, we also got a benefit. The benefit was smaller, about only 0.2 degree, but even in Houston, the cooling basically wins over the moisturing. Now, also in this case, we wanted to understand at what rate should we inject the mist. If you inject too little, basically you will. If you inject too little, you will not get enough cooling. And if you inject too much, you also would basically waste this moisture because it will fall onto the ground. And it turns out that optimal misting rate is actually dependent on the wind speed. So this is an example or a plot of the average drop in canyon air temperature as a function of wind speed. Let's focus on the red one, which is the misted section. You see that basically there's an optimal optimal wind speed. If the wind speed is too low, the air in the misted section gets saturated and basically you don't get evaporation anymore. And if the wind is too high, this advective warming becomes very strong. So the cool air is basically removed very rapidly and you don't get optimal cooling. So for this misting rate of 0.1 liter per minute, we got an optimal wind speed of about, this looks like if almost 4 meter per second. And again, you can now basically look at the optimal flow rate as a function of the wind speed, and the higher the wind speed, the higher the flow rate you can accommodate, and eventually it asymptotes. Okay, I'm going to skip this slide in the interest of time. And I'm going to go to talk about the last range the last family of solutions that we're looking at. And this is related to urban photovoltaics, which are becoming more and more common these days in cities. And so we wanted to understand how they would impact urban microclimate. And specifically, we were interested in what is the difference if these panels are adhered or basically in contact with the roof, if they are elevated but the edges are closed, so not ventilated, if they're elevated and ventilated, and if they are tilted. So we wanted to look at how these different design decisions impact the urban microclimate. So here we're going to solve again the surface energy budget for each surface, the roof, the top of the panels, the bottom of the panels. The only difference here is that we have this power production or electricity production term that is basically an energy sink in the surface energy budget. We evaluated the model against observations for the top and back surface temperature of the PV with data we collected over Princeton, and the observations are quite, or the validations are quite good. What was very interesting here in the results is the extent to which these design choices really make a very big impact about how photovoltaic impact the city. So as a reference, we had a black roof and a clean cool roof, so a white roof. And I'm showing you the ground heat flux conducted into the building during the day and at night. And I'm showing you the 4 designs. So what's clear is that basically all 4 designs of PV perform much better than the black roof. So from a building energy consumption perspective, they are very beneficial. And even some of the models that, for example, the tilted solar, because there's a strong convection and cooling where this heat is shed to the air, the heat flux into the building actually becomes smaller even than a cool roof. So from a building energy perspective, it is extremely beneficial. Now, of course, that heat is not disappearing, that heat is being convected into the air. And what we also observed is that photovoltaics will have the impact of increasing the daytime urban heat island, but actually decreasing the nighttime urban heat island because of the drop in storage. So the various designs partition energy very differently. The design and layout were even more critical than some of the panel properties we tried to vary depending on the panel design itself. And all designs are better than the dark roof and reduce storage significantly, but they also change the whole diurnal cycle of the fluxes. So finally, one of the things we are trying to also look at now is how this emerging mobility in terms of sharing of the cars, the micromobility, the electrification, and and finally the autonomy, how are they going to impact the urban environment? So we want to harness the urban livability and environmental opportunities of these emerging mobility solutions. So this is very, very fresh results. So we're starting to get them, but they're very exciting. So I'm going to share them with you. This is analysis of a range of cities, and this is the baseline concentration of ozone and PM 2.5. Here, obviously, we're using WRF-Chem. And what we observe here is basically for the most optimistic scenario where we have full electrification and where sharing is decreasing, the vehicles might travel per vehicle, we can get actually a significant drop in air pollution in these cities if we allow this basically mobility transition to play out, and if we guide it using adequate policy. Also, that is resulting in cooling that is not negligible. So, for example, if you focus on the daily average cooling in the urban core, not average or over the city, you can reach not reach but get close to a degree, 1 degree Celsius of cooling, which would be very important. So finally, what are the takeaways? So cities and built terrain more generally are an emerging anthropic and earth system that will be critical for humanity to understand and manage in the coming decade. This polysphere is quite complex due to the form, fabric, and function of urban land and multi-scale physical interaction with other Earth spheres. Urban models, however, have come come along a great deal in the last 2 decades. When I started working on this, the models were starting to come out, but they were very rudimentary. Today, we have very sophisticated models that are also coupled with a range of weather and climate models, and so we were able to do much more in terms of urban climatology. And the exciting part is now we can use these models for prediction, not only diagnosis. So for prescription, not only prediction and diagnosis. So we are starting to be able to use them to actually design more sustainable and future cities. I had a few extra slides that I'm going to skip about what's next. Maybe I'll summarize them very quickly. So in terms of Earth system modeling, we're going from kind of separate models at different scales to kind of integrated unified models. So one of the challenging on the modeling side is how do we continue to develop these urban models that will work across all scales and in models that are either at the global scale or at a very fine scale. Also, what is the role of AI and machine learning? So for example, this is a machine learning model of Landsat. On the right, I have the model, and on the left, I have Landsat, and they basically match quite well. So the AI tools are coming a long way. And again, we have a lot of exciting emerging applications in terms of solutions, whether basically thinking about new type of material or solutions that combine shading and power production or shading and ventilation. Again, I will skip some of these, but I have to go back to thanking my students and postdoc who do a lot of the heavy lifting. I have to also thank Princeton, NSF, NOAA, and the Army Research Office for funding us. And if you want to learn more about our work, please go to our website and see all the exciting stuff we are doing. Thank you.
Thank you. So if you have a question for Professor Bou-Zeid, please raise your hands now, and I can call on you. And if you do not have a microphone, or if you just prefer, you can type it in the chat and I'll read it out loud. Let's go ahead and start with Mark.
Oh, hey, hi, fantastic talk. Thank you so much.
Thank you.
One of the challenges that I'm sure you're aware of in doing urban modeling for the meteorology are things like the turbulence and mixing, vertical mixing, horizontal mixing, which will impact, all the phenomena that you've been talking about. Have you done any work trying to link sort of the microphysics up to the larger scale, or how important do you think that is?
Yes, we have done a lot of, the way I started working on urban climates is looking at basically flow and turbulence and large eddy simulations in cities. I have to say, I haven't, we could have done much more in terms of linking and translating things from the micro scale to the mesoscale, and taking what we're learning from large eddy simulation and translating it into better UCMs. Unfortunately, I haven't done as much as I would like in that regard. But some of my students, like Chile, who's you see in the figure here in the back, some of my ex-students are doing better than me now and doing some of this work. But there is a lot of opportunities to really improve our understanding of flow and turbulence. Now we have really some very good tools to do basically simulate and understand flow and turbulence at the micro scale, and then how do you translate this to better parameterization in urban climate model. I think we're the community is starting to do that, but there's a lot more work to be done, but it's doable.
Thank you.
Thank you. So Dr. Elie is next.
Hi, can you hear me?
Yeah.
Yeah.
Oh, yeah, great talk. Indeed, enjoy very much. For urban modeling, there's so many factors that could affect urban, temperature, precipitation. So first of all, when you validate your data, how do you validate what kind of data? Just ordinary weather data in cities are very limited. The ideal case, you will have a temperature, rainfall on different structure, different height. That kind of micro meteorological data will be very needed. Secondly, underground information, especially for your runoff data. What's the pipeline structure? All these three-dimensional data could be classified data, especially for some countries. They may not share such highly sensitive data. I wonder how much such data you can get. My second question is about urban have so much use of energy due both industry and also residential heating, etc. That kind of effect are your model be able to simulate?
Thank you. Those are extremely important questions. So first, how do you validate? This is always a very challenging question, right? So a lot of our validation, we tend to deploy our surface temperature sensors. Those are very good because basically when you compare the surface temperature, it's localized, it's the temperature of that surface. So when I was showing, if I go back, for example, when I was showing some of these validations, let's say here, this was the surface temperature, and we could compare asphalt to concrete, to vegetation. And so that's kind of a surface temperature, and is an easier thing to compare. When it comes to air temperature and the 2-meter air temperature that models give, in fact, this is very tricky, and we basically have shown that the default 2-meter air temperature that you get is sometimes not very correct. And also when you have a 1 by 1 kilometer grid, and you compare the average 2-meter air temperature over that grid to a specific station that is in a specific location in this 1 by 1 kilometer grid, there could be large differences because of the heterogeneity of air temperature in the city. So typically, for example, in the Brooklyn example that I was showing here, what we are comparing is basically there are a sensor network over Brooklyn that is measuring temperature at specific locations. And so we can match spatially, we can match the air temperature observation to the model prediction better, and we're doing some sort of these comparisons. So the validation is always tricky, and one has to be very careful in what output of the model you're comparing to what measurement. I would have to say that basically in terms of the density of observations, we again have come a long way. So ASOS stations, for example, are very useful, and we continue to use them. But now there's a lot of intensive urban campaigns that have collected urban temperature at much better spatial resolution that we can use in validating the model. So we're no longer kind of stuck with weather data that is still kind of designed for synoptic and mesoscale models like ASOS, despite those being very useful. Now, the other question was about the properties, and that is always a big problem because the city is highly variable, and everything varies everywhere in the city. The soils are unnatural, and so we can develop these models with all the fancy physics. But one of the question is, how do we get the inputs that can really represent represent the city properties correctly. That remains a significant challenge. We're getting better at it. But I would say that maybe here is where AI and machine learning can be extremely useful. So typically, when I want to model New York, I have to know the color and albedo of every roof in New York. And I need to know basically how many cars are in the streets and where are the trees and all of that and the height of the building. So it becomes a very data intensive endeavor. What we did in this application is to say, okay, well, let me just take a visible image from Google Maps of the city, in this case, Newark. Let me take just this image and assume that that image encompasses or encodes all the important urban properties and variables that usually would take me a long, long time to collect. And what we did is basically train the machine vision to model to take the visible image and very coarse resolution atmospheric data on the order of 100 kilometer, and basically use the machine learning model to downscale this coarse data to basically Landsat resolutions using just the visible images. And as you can see, it did very well for Newark, and with a little bit of retraining, it did also very well for Chennai in India. So the problem of inputs in urban models remains a large challenge. I would say that one of the things we can rely on maybe in the future is more kind of machine vision. We were never able to really use visual information in urban models. Now with AI and machine vision, we can use this visual information without truly digitizing it into building height and tree fraction and all of that, and just use it directly in our modeling. So maybe that will relieve some of the input challenges we have in model and cities, especially cities in the global south. And I think that answers your second question, or did I forget something?
Yeah, that's very good. Thank you so much.
Thank you. Do we have any more questions? Still have a couple minutes. Oh, there's a question in the chat. Are you planning or working on parameterizing those micro-scale urban features for the regional and global models with which you opened your talk, such as accounting subgrid scale eddy for regional model scales, for example, 1 to 4 kilometers?
Yeah, before I actually move, I think there was another question before about the anthropogenic heat emissions from buildings and cars. In fact, we do account for those, and one of my students now is working on actually kind of adding an indoor building energy model to predict the energy released due to heating and cooling, and the ones from transportation, we can also add it. Now, going back to the question of the microscale, let me see if in my backup slide I have anything that might be useful in answering that question. I'm gonna go through them. Okay, well, maybe that's not a good model. Okay, I'll take you, for example, to this video. This is a video that starts with flat roofs and then goes to angled roofs and then to round roof. It was basically collected in a lab by my ex-postdoc, Maider Yaguno, who's online now. And hi, Maider, she's now at UC Louvain. So what you see is the small, even a small change in the shape of the roof affects the flow and the turbulence significantly. And as a result, basically, even these minor changes in the form have a big impact on eddies and the exchanges between cities and the rest of and the atmosphere aloft. I don't think I have any backup slides to help answer this question, unfortunately. But the bottom line is what we can do today. What we can do today is do very realistic large eddy simulations that are resolving the buildings and resolving the turbulence in the city. and basically resolving, for example, the impact on turbulent exchanges between the canyon and the air above of a roof or a tree or anything like that. Now, we are doing these simulations. The question is, how do you take those and now use that fine scale data to develop or improve the parameterization in the coarse atmospheric models? So it was also kind of similar to the first question where I wish we had done more. I could blame the funding agencies that didn't fund my proposal, but I first and foremost maybe blame myself for not pushing on that a little bit more. This is an important gap that we still have. And we did a little bit of that. I think my lab and the community in general should do much more, because now we're able again to capture these micro scale very well. And we need to put a bigger effort into translating that turbulent eddy and turbulence and microscale understanding to better urban canopy models. So that step is still lacking. Some people in the community are starting to do it. I think there's much more that can and should be done.
Thank you. So that is all of the questions that I have, and it's right about at 3 o'clock. So thank you so much for everybody for coming, and obviously the biggest thank you goes to Professor Bou-Zeid for giving us this great talk. We will post this online within the week on our YouTube channel, and otherwise we will see you next week. Thank you so much, everybody.
Thank you, everyone, especially John and Casey.
Thank
Bye-bye.
you.
Bye-bye.
Have a good afternoon.